Okay, guys, welcome back. Let's start for today. As I mentioned before, my goal today is going to be to cover classifiers, classification, supervised learning, and the libraries. Obviously, my goal is that you are going to be able to implement some classification things later. Next week, my goal is to finish with random forest as the embed approach. And then hopefully we are going to have enough time to do a quick review in our last lecture. I want to put all the elements together, show you some examples of what you are going to have in the final exam. Final exam, we are going to post an announcement, but hopefully you are aware your final exam, according with the ASU calendar, May the 3rd is our exam, the final. The exam time you need to review on the web page. I am going to post the announcement later, but just be aware that could not be during our normal time in the lecture. The calendar, the date, ASU create that calendar. So the idea is that you do not have any conflict with other exams. If you have any conflict with other exams, talk with your other instructors because that is our time, period. Good. Now, for the last topics, classifiers. We start in the previous lecture with this idea of classifiers for text mining. We didn't saw anything. The only thing that I showed you in the previous lecture is, oh, there is an object there, naive base. Bayesian network for classification. But it was one object that we used. Let's talk about them, how to use them for a different thing that use text classification. Moreover, a little bit about how they work and what they are. So for classification, looking to our picture, the table of content, we're going to talk about supervised learning. I am going to talk mostly about classification. Some of the methods apply for regression. I am going to talk about the difference between those two. But basically for the practice purposes, I am going to be covering classification algorithms. In particular, I care about decision trees, naive Bayes, and hopefully we have time, SVM. But at least those two naives, the one that we used before, and decision trees, because I want to move to forests. Good? Classification, supervised learning. Why regressions and why classification? What is that? Okay, remember, supervised learning is the easy one of the machine learning. Is I have inputs, I have the outputs, and the only thing that I want is to figure out an equation that connects those two. Guys, there is nothing about learning, really. It's just about create an equation, figure out an equation that connects the input with the output, and therefore for you as a software engineer to implement the equation, or to implement the method that figure out the equation. And as you're going to notice, most of the work is iterations and calculate some numbers with predefined equations. Most of the equations, they are probability, math. They exist from the 1850 or something. It's nothing new, nothing computer science, but math and statistics. Anyway, putting together with a computer, they are supervised learning. Classification and regression. You notice two different parts of the tree. Oversimplifying the definition. We talk about classification. If we have inputs and we're trying to figure out a class, yeah, a discrete value. Yeah, I have the values and I am trying to figure out, is a good student or a bad student? I am trying to figure out, is this a table, it is a computer, or it is a chair? The number of classes is a finite number. Moreover, it's an integer number. Is 1, 2, 3, 4, whatever that 1, 2, 3, 4 mean. If you're looking for a discrete value, a class, you are doing classification. Now, what if what you are looking for is not a class, not a discrete number? What if what you are looking for is a value that is not discrete, a value that is continuous? Let me give you this example. Classification could help me to know if your final grade is going to be A, B, C, classes. Regression can help me to know what is going to be your grade from 0 to 100. Okay, you're going to get 99.8. Here, 71.5. A continuous value, an equation that gives me the value, not only the class or the category. Yes, oversimplifying, big two differences. Continuous value, discrete value, makes sense? Okay, Professor, but if for the grades, we do something with regression, if we calculate my grade from 0 to 100 as a continuous value, that could help me also to connect with a particular class, right? Yeah, you can transform a regression problem into a classification problem. Or the opposite. If you have a class, you can figure out a particular value, not the exact value, but a particular one. Classification, regression, discrete values, continuous values. Can we change? Can we connect, make one the other? It is always possible. Which one is the easy one? The easy one, the one that you can trust. Probably classification is easier because you are looking for a group of values. I am looking if you are A, B, or C students. That is easier than trying to figure out your exact grade or predict your exact grade. Good. Classification. Let's review for that problem some approaches, algorithms. And again, a fancy word that I put there for you, discretization, the last one. What is that? Discrete values. If you have a regression problem and you transform to classification, what you are doing is continuous value to discrete value, discretization, whatever. Review classification. Remember, the only thing that we want to do with pictures is you have your X and you want to figure out an equation that connects new or future X with the class, the Y that correspond, right? As usual, I am going to have a bunch of X. And with that X and the Y's that I already know, I am going to figure out the equation, my model. And later, I am going to evaluate that model with what? New X. And with this new X, I am going to predict the Y. And with this Y, I can compare with the original one and then get a report of the error. Fancy names for the variables, my inputs, my labels, my classes, the Y's. Okay, how do we do that equation? What options do we have? Do you remember this slide from the previous lecture? Text mining, and I give you the source code for the text mining. But if you notice there, where is the machine learning part? It's only these lines. Everything else was reading the inputs, cleaning the inputs, other things. These two lines was really the learning part. The learning part, it didn't happen in my source code. The learning part is this black box, remember? And the black box, according with this, looks like in that library, you have a class that looks to be a classifier parent, and the class was naive base trainer. So you have a class that for some reason have this name, naive base. And if you notice in my previous slide, naive base, one of the methods for classification supervised learning, right? So what you did in text mining, the previous lecture, is to use that method to classify different documents in a particular category. It could be a good idea to take a look into the black box and talk about naive base as a classification algorithm. What is happening inside of this object, the method train that we create with the library Manlet. Again, we create that object and we use that object for classification of documents. But again, classification, inputs and outputs, an equation that connect them. Before, we reviewed the example with documents, but could be anything. Let's review the general global idea. Naive Bayes. Key elements for the definition. Number one, good choice for a lot of data. Good choice if you care about the speed. When you care about the speed, when you want to create a model in real time. One of the good approaches, if you want to be updating your model in real time, learning when you are working, one of the approaches that allow you to do that fast, this one. Remember, you can do classification with neural networks. The problem is the neural network need time to be trained. A lot of calculations that you are doing, remember? You can create a neural network model, yes. Train in real time a neural network model. Maybe you need a good computer. Something that you're going to notice with this one, I am not telling you that this can compete with the neural net, different approaches. What I am telling you is this one is good enough in some particular cases. Moreover, this one by far is fast to train than the neural network. Why? Because you are going to notice the kind of equations that we're going to run here compared with the kind of equations that we run before classifying things with neural networks. Fast and easy to use with a lot of data. I am talking about the data for the training. I don't care if I have a lot of data for training. Why? Because I am not going to process row by row like I did with neural network. Here, the approach is going to be a little bit different, easier. Moreover, you're going to notice that here, there are two important names, Naive Bayes. The second one is the name of the guy that is giving us the equations to work, in particular, a theorem. The first one is because one small thing. This approach assumes the following. All the X are independent. So it doesn't matter if I change one, the others do not get affected by that one that change. Every X is independent, and therefore you can calculate your output, and the change in one column doesn't mean that the other columns are going to change or are somehow connected. Why we think about this as naive? Because that is not true. That is not true. Let's go with my example of your grades. If I use naive Bayes to calculate your final grade, categories, A, B, C, using this approach, I am assuming that your grade in the midterm or your grade in the homework 1 or in the quiz 3 or whatever, each column is independent from the other columns. Is that true? It's an assumption. In the reality, they are not independent. Think about it. If you get 80 in the midterm, what are the probabilities for you to get 80 in the final? There is a correlation there. Yes, you can get 0 in the midterm, and then you can get 100 in the final. Is that really true? You can get 100 in the midterm and 0 in the final. Is that really true? We can make the assumption that yes, it's true, and therefore I can use this approach. And for some problems, like maybe your grades, it's going to work. But it's a naive approach because I could be naive thinking that a student that get a 0 in the midterm suddenly get 100 in the final. Be honest, that do not happen unless something there, right? I am talking about your grades, but you can think about any other problem. Usually the columns, some of them are one way or another connected, even though we can think or we can be naive, assuming like they are not connected. I can make another example. What about your GPA? You can have your iPods, and in your iPod you have your grades. And in your grades, each grade corresponds to a particular class, a particular course. And then you have your GPA, and your GPA is the average your courses, right? And tell me, one grade in a particular course is independent of the other courses? And theoretically, naive, yes, all my courses are independent. Really? If you get a low grade in a core class, that one is going to be independent from getting a good grade in another class. Moreover, think about the instructor of the class. Is independent? You can be naive and say, yes, it's independent. It doesn't matter who is teaching the class. The grades are going to be not related. You know that that is not true, right? Okay, naive. That is the reason for the naive word, assuming independence. That is not exactly true for most of the cases. However, you can assume that. And in assuming that, you are being naive, but you are facilitating some calculations. Which calculations? The theorem of the guy. What is the theorem? Very simple. All the machine learning or all the learning here is this equation. Addition, multiplication here, and a division. Really? Yeah, three things. Multiply, divide, done. That is learning. Yeah. What is this? Let me talk about base. Notice that I am showing you an example used to start with only one X and one Y. This is naive base? No, this is just base. Why? Because I am not being naive. Why? I only have one column, so I am not assuming independence. In order to assume independence, I need two columns to assume that one column is independent from the other. This one is just base. One column is alone, so nothing to compare. No naive assumption here. What is this guy telling me? This guy is telling you the following. Give me inputs. Give me inputs with X and Y. And then help me to calculate the following data. Help me to calculate literally averages. Help me to count the data. How? Yeah, let's start with frequency of things. Frequency, counting, counters. Tell me for the labels, the output. Here I have yes and no, right? Okay, tell me for the yes and for the no. Yes and no, two columns. Tell me your X. These are my X. The different X, how many for each of the different values of the X, how many instances you have in the outputs? So for instance, if the input is rainy, how many times for rainy you have a no as a label? How many times for the rainy you have a yes as a label? The same for all the different inputs. Do you think that you can do a program, a computer program that read the data, whatever the data is, search for the different inputs and the different labels, create a table, and then fill this counter? How many of and the intersection of the two? Trivial, right? Okay, step number one. Step number two, you have the numbers. Help me to make some calculations. Calculations, probabilities. Probabilities, for instance, you are telling me that in total, what I have in my inputs is 14 values. 14 values, and you notice that 5 values have the label no, and 9 values have the label yes. So those numbers, 14, 5, 9, they are important. They are totals. You are telling me that, Rainy, you have 3 no's and 2 yes. So you are telling me that the sum of those yes and no, the total number of Rainys that you have here is 5. 5 of 14. The total number of overcast that you have is 4. 4 plus 0, plus 0 of 14. The total number of inputs divided by the total number of entries. We did that before, remember? That is the lines. What about down? Similar idea. You are telling me that you have 5 nodes in total and 9 yes in total, and the total is 14. So 5 divided by 14, 9 divided by 14. All those numbers are relevant. And the only thing that they have there is the numbers as a fraction. Easy to identify what is happening, and the number as a decimal number, used because we're going to use those in some equations. That's all. Yeah, that's all. Create a program that is able to identify the different inputs, the different outputs, and create those tables. Calculate the counter, and then calculate these divisions that are kind of my probabilities so far. And what I can do with that, then you can apply the equation. The equation, yes, the equation is going to help you to calculate the probability of something happening giving some input. Like, for instance, okay, you know what? My input is here, this. There is a sunny day today. Tell me, the label for that input is going to be yes or is going to be no? What do you need to do? Easy. Calculate the probability for yes. Calculate the probability P no giving the same input, and you are going to get some numbers. Yes, those numbers, probabilities, 0 to 1. And the only thing that you need to check is which one is higher. And the one that is higher, that is the label for that input. And I didn't put the calculation for the no. You can make it. But if I am calculating the yes, and I get something that is higher than 0.5, looks like that guy is going to win. So what I am getting, applying the equation, is like, according with this input, and with these frequencies, and with that table, if I get this input, the output, the label is going to be yes. What does it mean, the input? What does it mean, the output? I do not know. Is what you give me here, and I am telling you what is going to happen with your new input according with the data that you give me to review. What? Yeah. What is the probability according with the equation? The class, the input, one input. The equation is the probability. Notice that these two are the opposite of these two. So the probability of this giving the class and this is 3 divided by 9. Can you explain me why this is 3 divided by 9? Probability, SUNY and yes. Let's see, sorry, and yes. Did you notice that in the frequency we have 3 yes for that? Really? These two are my coordinates, the row and the column in a 2D array for programming, yes. Wait, but there is a division here. What is this 9? You can do a program that do that, right? The cell here, the total of the column. Okay. Multiplication, probability of yes. 9 divided by 14. Total in yes, 9. Total in. I can do a program that this. Divided by. Sorry. There are a total of 5. Doesn't matter in which. 14. Did you notice that when I do not have this given something, I am working with the totals? And did you notice that here, when I have given something, I am working not with the total, but with some intersection? Do it. number, high, that is your class. That is true. That is going to be the classification. Your input is going to be in that class. Professor, but the only thing that you have is the input, right? Yes, the only thing that I have is the input. This is the only thing that I have. I am searching for the class. You are going to search for this yes, and you are going to search for this no. You are going to search for both. Randomly, I start with this one, and randomly I get that number, and that number is 5. That is going to be the truth. That is going to be the one that I report as the class for this input. Very easy to program. Just follow the question we are done. Machine learning, yes. However, you are thinking like, yeah, well, it's just one column for the input, it's just one column for the output. That is not what we are going to have in the real world, right? We're going to have more inputs. We're going to have more X. Okay, we're going to have more X. Like, what do you want to do? You want to do X 1, 2, 3, 4, and the label. These numbers are just my Excel page, right? I have still the 14 inputs. Okay, now it looks like instead of having just one column, that was pretty easy, I am going to have 4. I am going to show you 4 just because that is the size of my slide, but hopefully it is going to be clear that the same process that I am going to follow for 4 can work with 5, 6, 10, 100, etc. Right? Okay, here we are going to need the naive. The naive, we are going to assume that this, and this are independent. So we're going to assume that even though here I have rainy is not connected with humidity or temperature. Is that true? We're going to be naive and we're going to assume that the temperature has nothing to do with the conditions of the weather, or the humidity doesn't have anything to do with the temperature, which we know, or we can be talking with an expert, and that expert is going to tell us, your assumption is not a smart one. No problem, naive, base, independent, all the columns. But now we have 4 columns and 1 Y. Things are going to happen. Yeah, things that are going to happen is that now, instead of just calculating these frequency tables for one thing, I am going to calculate frequency for several things. I give you some tables here, and hopefully it is clear that these are the counters and these are kind of the divisions that I have before. Exactly the same thing that I did with one table, but now I have several. We're going to go back to the tables. Just allow me first to introduce the equation, because now we have 4 columns. And my equations, the original one, the base rule, the above one. But now we're going to move to naive. We're going to move to several columns. Did you notice the difference? Looks like the yellow part, the one at the end, at the top is the same. Looks like the blue and the red, something happened. Something happened. Did you remember that before in base, the division was the probability of the input? X is our input. Did you notice that now it's not the probability of the input, but the multiplication of all the probabilities of the different inputs? So now it's going to be the probability of 1 times the probability of 2 times the probability of 3 times the probability of 4 for my 4 columns. And if you have 100 columns, it's going to be the multiplication of those 100 values, the last one, xn. The probability of, help me guys, why we are doing multiplication, not addition?
Probability is already below 1.
Yes. When you work with probabilities, what you do is to use the multiplication. We did that before, remember, softmax. Do you remember that in some point our equation changed to this guy versus this guy? Probabilities. With probabilities, You are going to notice your equations get multiplications, not additions. Again, we do not need to know the details, but remember that this multiplication helps you a lot. A lot, yes, because the number below is the multiplication of all the different variables. Now, what happened with the number above? The number above, you are going to notice, is also multiplication. Multiplication of what? In the original one, x bar the class. Now, x1 bar the class, multiplication, x2 bar the class, x3 bar the class, x4 bar the class. New equation, I think we can do it, right? I mean, the only thing is now we have more multiplications. Now we have more calculations to do, but the process looks to be the same. Now, where I am going to get the numbers? In my table there. And with the numbers that I have there, just like before, I can solve the second equation. And with that, I can get a final result that is going to be the probability of some input several values to match with the class that I have here. And I am going to get as many results as classes I have. And the only thing that I do is to select the biggest number and say that that is the class for that input. Do you remember that we did exactly the same with neural networks? The only thing is that we have a neural network giving me these numbers, the outputs, and then we select the highest one. So you are replacing a neural network with these tables in which basically you have these counting things and the division among the number of total inputs. Yeah. And you use those two approaches for the same? Yes. And which one is better? Depending on what you want. I can tell you that this one is faster. Did you notice a loop there? Or kind of calculation, iterations? We're going to do some loops there to do the counting, but by far, it's going to be faster than all the training that we have for the gradient descendant in the neural networks. Moreover, we can do this in real time. I mean, in real time, if you change the input data, real time, update the table, and your next calculation could be including the new data faster than the neural network. Is as good as the neural network? No. Why not? You are working with probabilities. You are not really training a model that matches the data. You are just thinking about how probable it is to something to happen according with the input data that I have. Now, here, for this approach, can you notice that something very, very important is that you need a lot of data? So this example that I am showing you with 14 inputs is going to be very, 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 very bad. Your probabilities, your divisions, a few values in a division are going to give you numbers that do not match the reality. Remember your quizzes? Day one, you get 0 in one quiz. And for Canvas, you have 0 points of 25. Your grade in the class is 75 below. By now, we have 6 quizzes, and each of your quizzes have a small number, a small value. So by now, even though you still have this 0 in the quiz 1, your grade is not below 75. More values, small impact in the individual ones. More data, small impact in the individual ones. That is the key, right? More data. Okay, no problem. It's going to be bad, but it's going to help me to explain. Let's see. What if you have the tables that I mentioned? You have the equations. And I would like to know that one. You know, today is rainy, it's hot, high humidity, and it's not windy. So those are the 4 inputs that I have in one new row. I already did the training. What was your training? Calculate the counting. That was training, the closest thing that I have for training here. I have my model. What is your model? The equation, the one that I show you, that is going to be the model for everything with the tables, with the counting. Okay, now tell me, if I have those inputs, what is going to be the class for that input? Is it going to be a yes or is it going to be a no? The yes and the no is for going outside, right? For go to play. Yes or no. What your computer is going to do, what you can do is, let's go for the equation. Let's calculate the probability of yes and the no for all these inputs. And what is going to be? You can notice for you to review my calculations, but it's going to be, okay, the probability of rainy with yes, time, cold, yes, time, high, yes, time, false, yes. Each of the input, x1, 2, 3, and 4, given that, yes. All of them, given that, no. Multiply it by the probability of yes, and multiply it by the probability of no, divided by rainy, hot, high, false, rainy, hot, high, false. The probability of the individual inputs. Did you notice that the only thing that changed is the blue one? Because of the class. The other things are kind of the same. So in a computer program, you can reuse the blue ones and probably the red ones. And then you do the numbers. And can you help me to figure out how do I know that rainy yes is 3 of 9? Rainy yes, 3 of 9. I don't know, maybe I need to review the table. Rainy yes, 3 of 9. Rainy yes, column and row. 3, 9, the total of the column. It's the same thing that we did before, right? You can do the different numbers. That is the reason because I put the equation there. I do not really care about the individual things, but you can figure out where did I take 2 of 9, 3 of 9, 6 of 9, 5 of 14, 4 of 14, 7 of 14. And the only thing that I need you to remember is 14 is the total number. And 9 is my total of yes. My total of no's was 5. 5 should be there around, yes. I have 9 in blue above. I have 5 in blue below. The only thing that you need are those tables with the counting and this equation, and then you are going to get this 0.3, 0.6. Which one is the winner? We're looking for the highest value, right? The only thing that we can, tricky part here is before we were working with this negative log likelihood or log likelihood, and we were looking for values 0 or close to 0, we're looking for what? The class according with this is going to be no, right? How do we know that that is correct? Check rainy, hot, high, false. Rainy, hot, high, false. No. Really? You use the first row of the training for the testing? Yes, just to show you what happened. Obviously, it's going to be correct. I use that row for the training, and then I tested with that one. It's working. The numbers are okay. Clear. Okay, number one, I can ask you to do a program to do all these tricky things. Don't worry, I am not going to do that. Better, we have libraries. I mean, really, it's a challenge in software engineering or in programming, even to implement naive Bayes. It's a program for 110 tables, counters. Nothing challenging there. Let's use a library. Do you remember that we create already a naive Bayes classifier using Mallet for the text mining? Okay, there is another library that we know that maybe also have a naive Bayes classifier, and hopefully you remember this weak library. And that one looks like a library that have a lot of things because we use for clustering and we have a lot of algorithms for clustering. But if you remember, that library also have things for classification, including this one. This one, so my source code for naive Bayes. These two lines are familiar. Really, again, you are creating an object. That object is from a class. The class somehow suggests the name of the approach that you are following, naive Bayes. You have the object. And then when you have the object, the next thing to do is to call a method. Call a method, the training method. What is the name of the method? Depending on the developer, but by now, hopefully, you know, it's a method to do the training, to build the classifier, to do the calculations, to do the math. And always, 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 you need one parameter as an input, the data that you're going to use. Those two lines to build this classifier, naive Bayes, the same thing that we did before, that the only thing that it's going to do is to create these tables, to calculate the probabilities, and to report to you, given one input, the label that corresponds, that is the one that has the highest probability according to the calculations. Trivial, right? Okay, something that you are concerned about it is good. The object, perfect. But that object needs to be trained. And in order to train, I need to provide data. And something that is my concern as a developer is the format of the data. How do I read the data and provide the data to this object so this object can later be evaluated? Evaluation down, reading the data above. Reading the data, let's check line 11 to 23. At this point, can you explain to me what is happening from the line 11 to the 23? Something familiar that we did before? Maybe. CBS loader. It's a class, right? It's a class. And what I am doing with that class? It's an object, and I am giving that object with a setter one particular parameter, an object file that is connected with a particular path, the path that I put above. Can you put all that in one line? Yes, I can put that in one line, but I put 3 lines just to try to specify all the different steps. The path is different from the CBS loader, that is different from the parameter that you said before, right? Okay, what I am doing, I am reading a CBS file. Which one? This one. Do you get familiar with this CBS file? The table that I showed you before. The 4 input with the label that is the output, and above the labels X1 to X4 and the label Y. So you put in Excel those values, those strings, and the header. Yeah, CBS file, whatever you want to use. You read the CBS file, done. That happened in the first 3 lines. Do you remember the class instances? The class that you use to store your rows, right? Instances, whatever is your object, equal to loader.getDataSet. The loader, read the file. Now, from that file, give me instances. Give me a data structure with instances. Give me a data structure in which you store the different rows. I don't care about the data structure or the format that you use to put that information in the memory, but I need the information in the memory, period. And the class instances is going to do that for me. Get the data set, and then the line 15 is good enough. But then I am going to complicate my life with the lines 16 to 20. Again, this one, 15, good enough. But in order to complicate my life, 16 to 20, what I am doing in 16 to 20? Okay, you already have all the data in the memory. The next thing is, are you thinking about do testing? And yeah, you put all the data in one file instead of split 2 files for testing and training. Yes, I put everything together. Okay, good. So what we need to do is to separate from all the data that I read, 14 inputs, 2 things. 2 things, yes, instead of having only 1 instances, I can create 2. Guys, you can have 2 files and you do not need all of this, right? You only do 2 times this, read 2 different files, you are done. But if you want to read one file, okay, I can split. But moreover, if I want to split correctly, I need to randomly select some input for training and some input for testing. Randomly, did you notice that I am calling there this random class from the Java util? So it's not machine learning, it's Java. What are you doing? I need a random number. I need a random number for what? As a parameter for a method. Randomize. Randomize what? My data instances. And then give me 0.66 of the inputs. Why 0.66? Just because I want. I mean, how many data do you want for training and how many data do you want for testing? 80%, 0.8, 60%, 0.6. Why are you using 0.66? Why not? At the end, what I am doing is to round the number. What I am going to do there? 14, that is the size, times 0.66. It could be 0.6, doesn't matter. And that is going to give me a number. That is going to give me a number, probably something like 9. So that means that the other number, or the rest, is going to be 5. So I am asking for 9 inputs to training and 5 inputs for testing. Remember those numbers, 9 and 5. What if I want a different number? Put a different thing there. Point, whatever. The recommendation, usually at least 80% of your data for training. That could be a good idea. But in this case, I have only 14 inputs, so I have almost nothing. So at least I am going to use 5 for testing. Still, my results are going to be bad, but 5 for testing and the others for training. Done. What I am going to get is 2 numbers, 9 and 5. And what I am going to do is 2 different group of instances, 9 and 5 inputs. After I am done with that, the next is, okay, one important thing to do. I could have done this after that, because that is important. Now, tell me, in your CDS, which column is the one that is the label? Which column is the one that we want to predict? And in my Excel, and that is the only reason because I put the picture there, the column with the labels is the last one. That you can agree is kind of a good idea, right? I mean, you do not put the label. Okay. Anyway, the last one, did you notice the parameter for that set class index, class, the label? Number of attributes, attributes, the columns. Why the -1? You are experts on this, right? You have been working with arrays for years. So you know that we start with the 0, and therefore, if I have 5 columns, right? A, B, C, D, E, 5 minus 1, 4, because the first column is 0, 1, 2, 3, 4. Column 4, that is my label. Done. I am going to build the model, train the model with the training instances, the 9 that are for training, and then I can do an evaluation with the others. The evaluation with the test instances. Evaluation. Again, what do we need for the evaluation? An object. An object from what? From where? A class for evaluation. And the class can have different names. For this one, we're familiar with this one because we used Weka before for other evaluations. So we have a class evaluation, and we're going to create an object evaluation. And for the object evaluation, we're going to need to pass first the original ones, and then the ones that we're going to use for the evaluation. The evaluation model. This class is for evaluating diverse models with diverse approaches. One of the things that this guy needs is the model that I am going to evaluate. And in this case, this is my model with this input data. And then I am going to print 2 things. I am going to print Tree of the evaluation. And I am going to print this matrix from the evaluation. The names of these. The only thing that catch my attention was summary and matrix. Can you imagine what matrix we're talking about? Because we are familiar with a particular matrix that works for evaluation, right? So if I show you the output, hopefully it's going to be something that you found familiar. Remember that I print two things, the summary and the matrix. Summary above, matrix below. Matrix A, B, A, no, B, yes. At least read my data and the program figure out that yes and no was my labels, A and B. So what do you think, good or bad? Question for your exam, accuracy here. 3%. 3 divided by, yes. How do you know? Because you remember the equation. 3 divided by 5 accuracy, that is good or bad? Okay, I mentioned it's going to be bad. 5 input for testing and only 9 for training is kind of nothing, and this is probabilities. However, you have the info. You know that this is bad because you have here in the diagonal 3 and you have outside of the diagonal the 2. So that is almost 50-50. It's pretty bad. But in specific, you know this 3 divided by 5 is kind of, you know, you are very far from it. Anyway, above, total number of instances, 5. Total number of instances, 5. Why 5? The total number of instances in the testing data set. And well, your results. The only thing here important for you is correct classification 60%, incorrect classification 40%. That is something that you can notice immediately. You're 60, you're 40. Very bad classification, but it's there. Clear. Okay, only one thing that maybe you are thinking about it, like, okay, yes, good. This works with CSV files, but we want to work with more data. And maybe you have more data in a CVS file, your own data, so you can just duplicate this kind of approach. What if you go online and you get data sets from the repositories that we showed before? I am sure that you already have several data with labels from those repositories. And this library in particular, the Wicca library, use a particular format for the data sets. Do you remember? We have these crazy files. And the only thing that you are wondering, or that you maybe want to change or update in my previous source code, is like, well, you use the CSV loader to load a CVS file. What if you do not have a CVS file, but you have a data set like the weather? That one is something that we used before, or some of you used before. What if you want to load that one? These are your instructions. Good news, buffer reader, that is Java, but good news, you can use the class instance and directly pass as a parameter a buffer reader that is connected with one file of this category, and the library know what to do. We use more source code for the CVS than the source code that we need for this particular format, because this particular format is part of the library. Makes sense? So can I ask you to do classification with naive base of something that you have or something that comes from the internet? And hopefully that is yes, of course. Clear? Good. Now, more. This is good. This is going to work in several cases. However, there are other ways to do classification, and I have time for this. Okay, naive base with a data set, classification easy. Yeah.
Just to summarize, in the training, we are looking at the inputs, And we are asking if output is yes or no, what is the probability of the input being a combination? And using that probability, we are testing the data to predict the output.
Well, we're doing the following. To summarize, a good question. Let me go back here. Steps. Number one, we have the data, right? Number two, with the data, we calculate these tables. That basically is counting numbers of how many cases do we have in each of these different combinations. Yes, no for one attribute, yes, no for another attribute, yes, no for another attribute, and the totals. This is the only thing that we do. The other thing that we have is the equation. Which equation? The naive Bayes. Which equation? This equation, the second one. So we have the data, we calculate those tables, and we have this equation. Done. Then we have input data for the testing. And input data for the testing could be whatever value you give me for the 1, for the 2, for the 3, and for the 4. For them, the input is going to be any values that we have in this table. So my only point here is x1 should be, must be, one of the values in that table. I mean, should be sunny, overcast, or rainy. I mean, the only thing is I cannot randomly include a new value there that was not in the training. So it could be whatever there. So I can think about rainy or whatever. For the x2, again, should be one of the values in the temperature table. Should be hot, mid, cold, not other. Which one? Whatever. I am going to select the first one. For the x, for the next one, need to be one of the values in the ones correspond to humidity. Which one? Whatever. Let's think about high. For the next one, x4, need to be one of the values that is already there. So could be true or false, my only options. So this is my input. I do not know if this input is in the data set. I do not know if this testing is also part of the training. I do not care. Because now what I am going to do is to replace these values in the equation. And yes, I should have the probabilities because, for instance, when I ask in the equation, okay, what you want to calculate is what is the probability with this input for the class to be yes? What is the probability for the same input of the class to be no? So I'm going to calculate both. I am searching for the highest value. Starting with yes, I am going to create one equation. With no, I am going to create another equation. Starting with yes, I am going to calculate the probability of yes, given that those vector of values. And that is going to be the probability of rainy, given that yes, times the probability of hot, given that yes, times the probability of high, given that yes, times the probability of false, given that yes. And those values, yes, rainy, yes, hot, yes, high, yes, false, those are the ones that I am going to search in the tables. So yes, I have the probabilities for these combinations with the input data, but I do not know anything about this combination that will be a new one, right? So I am calculating the probability of something to happen given probabilities that I have from previous events. Probability, a combined probability process. Make sense? And obviously I'm going to multiply for the probability of the class, that is yes or no, and divide by the probability of rainy, the probability of hot, the probability of high, and the probability of false. So it's basically the new probability calculated using all probabilities and the probabilities of the independent events. Yes, no, and all these separate. Better? Machine learning? Machine learning. Not really, right? I mean, compared with all the things that we did in the neural network, this is just solving equations.
It's a lot more transparent, right? Because it's just a function.
Yeah.
Okay.
The transparent, something that we criticize from the neural networks, and you have read about it, is everything happened kind of in the black box, literally, because even you as a developer, you have no idea sometimes how that is going to behave, because the behavior is a lot about the behavior of the gradient descendant. And if you put equations and constants there, you know that each constant can somehow move the equation in one direction and in the other. It's kind of hard to debug what data or which data is causing some particular bias. That is a critic for the neural network. The bias cannot be controlled, only providing with data. And sometimes you are not sure about which data exactly. Here, you know exactly what's going to happen because you can debug the equation. There is nothing in the back. There is no dependency of previous calculations. It's not like a history of W's and one W affects the next W. There is nothing about how many times you pass for the data set. You just count the numbers. And guys, to be honest, classification is one of those cases in which you are going to look to the data. And moreover, if you look to the tables, the frequency tables, you're going to be thinking like, really, this is obvious. Those cases in which you think, this is obvious. What we're using is equations to teach the computer how to express or how to calculate those obvious things that for humans happen. Classification is about those easy things. Not thinking or learning really involved. Sorry to say that, but it's just that. The equation, the number, and which is the highest number. Done. Easy to debug, easy to know what happened. You have full control.
Other tools for that, like tracing it with
other tools about libraries. You have Mallet with this library, you have the Weka with this library, and there is a bunch of others. Advantage with classification, basically any library is going to give you classification. It's becoming kind of common thing. It's very easy to implement. I mean, there is nothing harder. Even you can ask, I asked my 110 students to implement this. I do not need to mention that this bias theorem is just do the arrays. It's a practice for the arrays. Good. Okay, another one. This is kind of the good one. This is the favorite. This is the one that you are going to read in every single place just because it's easy and also it's good. Again, good in the classification part, good compared with other classificators. You cannot compare apples with bananas, do not compare with deep learning. So you are going to be disappointed. But that one is good. Now, another one. Decision trees. Decision trees. You know trees, right? I mean, software engineers inside of you is thinking like trees. That's a structure, easy ones. But we put decision there. Okay, decision. Let's see. A decision tree is a classificator. Decision tree or cards, whatever you read, is all about the following. I have data, and I would like to create a tree that if I move from the root to the end of the tree, I am going to pass for nodes that represent the input. So I am going to have, I don't know, X1 here, and I am going to move to something that could be X3. And then in some point here, I am going to have a yes or a no. Professor, are you going to cross all the values like X1, 2, 3, and 4? Maybe yes, maybe not. It is not mandatory. You are going to cross some nodes. And with that node, at the end, you have a result. It could be all of them. It could be one of them or some of them. But the goal is having a tree in which in the leaf, at the end, you have the labels. And in the nodes, you have the inputs. I have the inputs. Wait, but the inputs have different values, right? It's like if you have the input X1, you have different values for X1. If I remember correctly here, in the previous example, there were 3 different values for X1. Each value, a different path. Oh, do you remember that the first input was this sunny one, or overcast one, or something else, whatever. The input, the node, the paths, the different values. And you can create a tree with another input, with another set of values, and with a particular value here and a particular value here. Maybe you can already tell me that the output is going to be yes or no. Machine learning, create a tree. You are not going to create a tree. You are not going to review the data to see how to connect the nodes. You're going to ask the computer, here is the data, give me this. "14 rows that I gave you before, right? If you start playing with the 14 rows, you are going to notice something. Every time that the value in the first input is equal to overcast, the label is yes. Yes, you can go out and play. Something that you're going to notice as a human, if you review the data, something that the computer is going to notice is, every time that you have here in this column, the first column, this value, the label is yes, so I can ignore the other columns. The only thing that I am going to do as a computer is, if you tell me that the outlook, the first column, X1, is overcast, the label is yes. I do not need to review anything else. Wait, no. If you tell me that the value for the first column is different to that, maybe this, or maybe that, raining or overcast, then let's see. Let's review those rows. And something that you're going to notice is, if the first one, the column 1, is sunny, and then you go to the next column and you check for humidity, basically with humidity high and value sunny in the first column, you're going to get a no as a label. But with the normal here, you're going to get a yes as a label. So with only 2 columns, you can also decide yes or no. So if you have overcast, one column tells you the yes. If you do not have that one and you have the sunny one, the other column, the next one, is going to tell you the yes or the no. Okay, what happens if I do not have the sunny one or the overcast one? What happens if I have raining? You continue searching, reviewing your data, and the common sense is going to tell you, if you put Excel sheet and you classify the things, you're going to notice like, did you notice that when we have rainy here at the beginning, and this third column or fourth column, if we have true or false, always when we have rainy true, the label is no, and always when we have rainy and false, the label is yes. Common sense, right? You're searching for combinations. You are creating in your brain a tree like that. Now, the question is, do you think that we can create a program that creates that tree? It is not as easy as the naive base. Believe me, it's not as easy. But I think it's possible, right? What would you do? Divide and conquer, right? What is my first problem? You are asking me to create a tree. My first problem is, which of the attributes is going to be the root? Yes or no? Problem number 1, what I am going to put in the root. And then I can recursively say, okay, I have the root. What is going to be the next one? And the next one, and the next one, until every single combination is covered, and I have just yes and no, the labels in my list.
You want the root to be the most significant factor, I think, the most deciding decision making.
Yes. The question is which one I want as a root, and that is my answer. The root should be something that really split the data in 2 different branches. And what do we do in order to find which one is our candidate? This is my data, right? It's the same data that I use with bias. You know the data, 14 data. You know what I am going to do? The same thing that I did before. let's think about using the column 1, x1, as the root. Okay, tell me how many different values I have in x1? 3. Okay, 3 branches. Okay, let's assume that you split the data only using the value in that column 1. And if you split the data, do you remember that we have so far 14 rows? So how many are going to be here, assuming that the value in the first column is sunny? How many are going to be here, assuming that the value in the first column is overcast? How many are going to be here, assuming that the value in the first column is rainy? This is the number of labels that I am going to have. Not only the number of labels, but which labels I am going to have, right? Again, you have your input. The only thing that you're going to check is sort by the first column if you want, and you're going to notice which labels you have connected with each case. And those are my labels. Humans, did you notice something there? Obviously, I am going to do exactly the same using the second column as the root, the third column of the root, and the fourth column of the root. I am doing exactly the same, assuming that this column is going to be the root. What is going to be the division? This column is going to be the root. What is going to be the division? This column is going to be the root. What is going to be the division? And those pictures show me what are going to be the division. Notice that the last two have only 2 values, false and true, high and normal. The others have 3, hot and cold, and the ones that I already have. I check with all these guys as the root. All of them, I consider them. And I choose X1. I choose this column called Outlook. Remember, my table, Outlook here, the second column, sunny, overcast, rainy, those are the values. And I choose that one as my root. And the question is, why? Why I like that one, not this one, not this one, not this one? There is one reason.
Because yes and contrast.
This is perfect, right? Any other option give me something like this? This is good. Wait. Obviously, this was an easy selection because you have this one that is perfect. So that is kind of the highest, the good one. What happens if I do not have that one that is perfect? Which other could be a good candidate? And here, what you are doing is searching for how many different values, yes and no, you have in each of the branches, right? You are looking for how different the groups are. And obviously, you are looking for a good one that split the things in different groups. You are looking for a good choice of something that split the groups according with this idea of how random or not random are those groups. And you know what? What you're looking for is for a measure that have a name. Entropy. What you are doing, your brain is doing, what the computer is doing, is going to do for you is literally to calculate the entropy for each of the different groups that the variable is able to create. Did you notice that before we calculate the probabilities for each of the groups, we calculate the probabilities, we count the number of sunnies and overcast and rainy, and we divide it by the total number, la la la. Now, we are not using probabilities in that way. We are not using that equation, but we're creating these groups. And for the groups, we're going to calculate a number. And now the number is going to be a measure of the randomness of the group. How different are the elements in the group? Fancy name, entropy again. And something that we're going to find is the entropy values for this particular option here is going to be good. And the reason because it's going to be good, I need to talk about the value, but the good is this guy is going to put the good above. because that guy is like, good, you put this as the root, and you are going to have what I showed you before. You are going to have this tree in which from the root, if you have that value, immediately, yes. Because all the elements in that group are yes. And I am sure that you are thinking like, yeah, but that is true only for the data that you use as an input. I mean, that doesn't mean that that variable is a very good predictor. That just means that in the input data, all your data have this match. That is your problem, guys. You need to provide enough data, a good data for the input.
So are we looking for a candidate which will give random values in the group or not random?
The opposite. We are looking for a candidate that gives us separate groups, and the randomness between the groups or the difference between the groups is a good one. So I am looking for values that give me a group that is mostly the same elements or a few variation between the elements. Obviously, I choose this one because in the middle, all of them are the same. But if I do not have all of them the same, what I am looking is, okay, it could be good to have like one that is different or two that are different. But 50-50 is not a good predictor. I am looking for something that really split the data. I need to talk more about how do you calculate entropy and what is entropy, but that is what the computer is going to calculate. What you are looking at, all are the same, that is great, and that is going to be a number. Clear. Okay, guys, I am stopping here. We continue with this next lecture. Thank you.